All right, let's get into today's lesson. We're going to learn factor numerical and algebraic expressions, and we're going to be able to write equivalent numerical and algebraic expressions. Write this down along with today's date and page number before moving on. Here's your warm-up today. I have 5 different scenarios where you just have to find the greatest common factor. Use one of the 2 methods that I taught you in the last lesson, and let's see how you do. 2 of them probably threw you off and realized the only number that is largest that they have in common is 2 with question 1 and 4. For 2, 6 was the greatest common, 3 was 15 being the greatest common factor, and for 5 it was 8. So I hope you got all those correct. If you did get all of them correct, give yourself a pat on the back. Now that your brain's warmed up, let's move on. So let's go back and review some of these terms that we've had, vocabulary that we've had previously. I do want you to write these down. So the terms of an expression are parts of the expression. So the terms are the parts of the expression that are added or subtracted. Okay? So the terms of this expression that I have here is 140 plus 4x. So 140 and 4x are the 2 terms that get added together. Now the 4x part, that can be broken down to show that the x we know is a variable, but the 4 is called a coefficient. And a coefficient is the number that is multiplied by a variable. So this is information we need to know because we're going to be working with this using the distributive method and greatest common factor to try to solve some problems today. So go ahead and write these down before we move on. Our ultimate goal today is to be able to create equivalent expressions. And what these are expressions that, if written differently, still give you the same value. So the example I have here, and that's all you really need to know is that definition, but you should put this example in. 15x plus 18 and 3 times 5x plus 6, these are both equivalent expressions. They have the same value. That's what we're going to work on today, learning how to do. And we're going to slowly break it down. We're first going to look at numerical expressions, 2 numbers. Then algebraic expressions, numbers with variables. And then how can you write multiple different ways of expressions, which are equivalent expressions. Now, to do the greatest common factor and the sum of these 2 numbers, I encourage you to use the prime factorization method to find the greatest common factor, but you don't have to. So first, if we look at this, we see 27 plus 39. If we were told to pull the greatest common factor out of these 2 numbers, I used the prime factorization and I broke down the number 27 into 3 times 3 times 3, or at least the factor tree did. And then 39 was broken down by 3 and 13. So the greatest common factor of these 2 numbers is 3. So the 3 gets put on the outside of using our distributive method, outside the parentheses. And then what you have to do is multiply up what you have left in each term. So what was left over that couldn't be shared was a 3 times 3, which is a 9. So 9 gets dropped down into the parentheses. We're still adding, so that gets put down all the way here. And then all that's left over is 13 here, so the 13 goes into there. So we were able to pull out the greatest common factor and see when you pull the greatest common factor out of 27, being 3, you're still left with 9. When you pull 3 as the greatest common factor out of 39, you're still left with 13. 27 plus 39 and 3 times 9 plus 13 are the same thing. They're equivalent expressions. And the way we can prove that is by solving it. 27 plus 39, what's that give you? 66. So 3 times 9 plus 13 should give us the same thing. Order of operations tells us to add 9 and 13 first, which gives you 22. Now you're going to multiply that by the 3 that we pulled out. And 3 times 22 gives you 66. So these are equivalent fractions, but they are equivalent expressions, but they do show the greatest common factor pulled out. Have this written down. I'm going to do one more with you before I have you do some practice problems. Now let me show you doing greatest common factor in a sum of two numbers, so breaking out the greatest common factor using the uh, list system of finding the greatest common factor. So let's first list the factors of 15 and 45 and see what we got. 1 goes into 15, 3 goes into 15, 5 goes into 15, and 15 obviously goes into 15. For 45, 1 goes into 45, 3 goes into 45, 5 goes into 45, 9 goes into 45, 15 goes into 45, and 45 goes into 45. So the greatest common factor that we have is 15. So when we rewrite the greatest common factor in the sum, we can write it as 15, and what goes in the parentheses? Well, 15 times what gives you 15? 15 times 1. So you're still left with 1 here, and we still put the plus symbol. Now, how many times will 15 go into 45? 15 went into 45 3 times, so that's left over here. So this one is written as 15 times 1 plus 3. Now, to see if that's correct, let's see if they both give you the same value. 5 and 5 is 0, carry the 1. 4, 5, and 6, you get 60. So here, with the new one that we created, 3 plus 1 is 4 times 15. 15 times 4 is 60. So this does work because it gives us the same value as the original one. Again, you can write this down if you want, but you do not have to. All right. I'll do number 1 with you, and then you will do 2 and 3. But if you want to try all 3, pause the video now, do 1, then you can come back and see if you're doing it right before you do the 2 and 3 on your own. So the first thing we have to do is find the greatest common factor of 16 and 12. So I'm going to use the list method because they're small numbers. 16, 1 and 16 work. 2 goes into 16 8 times. 3 does not go into 16, but 4 goes into 16 4 times. For 12, 1 goes into 12 and 12 goes into 12. Get the easy ones out of the way. 2 times 6 gives us 12, and 3 times 4 gives us 12. So what's the largest number they have in common? They have commons of 1, 2, and 4, 4 being the biggest. So first pull the greatest common factor out. Put that on the outside. And now, how many times does 4 go into 16? Basically, what's left over when 4 goes into 16? 4 goes into 16 4 times. And 4 goes into 12 3 times. Now, to check to see if this is right, let's first do 16 plus 12. That gives you 28. Well, what do we get down here? Order of operations is first. 4 plus 3 gives you 7 times 4, which is 28. So this is your attempt at writing the factor of the sum of the terms and its greatest common factor. Go ahead and try 2 and 3 on your own. Come back when you are done. So here are the results you should have gotten for 2 and 3. The greatest common factor of 21 and 9 was 3. So when we pulled that out, 3 went into 21 7 times, and 3 went into 9 3 times. So your remainder is left as 3 times greatest common factor, 7 plus 3. And for 3, the greatest common factor was 5. So you put 5 times, and what's left over when you put 5 back into 15 and 5 into 20? 5 goes into 15 3 times, and 5 goes into 20 4 times. So hopefully you got those 2 right. If you did, come on over and give me a high 5, and then you can continue the video. All right, now we're on to the second example. This time we're going to throw some variables in here and see what we get. So with this one, we can see that to find the greatest common factor in the sum, we're going to have to break down the greatest common factor of 12 and 28. And then B doesn't disappear, it's just going to kind of tag along. So if we broke down the prime factorization of 12, 12 is broken down into 6 times 2 and 3 times 2. So that's how we get 2 times 2 times 3. And then don't forget the B carries down there as well. For 28, when you break down 28, 7 times 4 gets you 28. 4 gets broken down into 2 times 2. So that's how I got 2 times 2 times 7 here. Now what do they all have in common? They share two 2's. A 2. So they share 2 times 2, which is 4. So 4 becomes our greatest common factor on the outside. And then now just look at what's left over. 3 and B are left over with 12B. So that drops down to be 3B. And 7 is all that's left over here with 28. So 7 gets put down here in the parentheses. And now you have 4 times 3B plus 7. And you can't add 12B and 28 together because 28 doesn't have a common variable. So that is the final answer of our problem. So the variables, don't let that trick you. You just kind of have to add that where it lies. Write this down before moving on. At least the work part, not so much the stuff in blue. All right, I'll do one more with you, and then we will move on to your practice problems. So let's find the greatest common factor of 16B and 32. We already see that we have a B here, and there's no B over here. So we know that whatever it is, the greatest common factor is going to be something with B plus something else. All right, so let's find the greatest common factor of 16 and 32. I'm going to use the prime factorization tree again. So 8 times 2 gets you 16. 8 can be broken down to 4 times 2. And 4 can be broken down to 2 times 2. So we have 2 times 2 times 2 times 2 is the prime factorization. For 32, you can get 16 times 2. And then 16, as we know, can be broken down to 8 times 2. 8 can be broken down to 4 times 2. And 2 can be broken down to 2 times 2. So we have 1, 2, 3, 4, 5 2's. 1, 2, 3, 4, 5 2's. They share 4. So 2 times 2 is 4. Times 2 is 8. Times 2 is 16. So the greatest common factor is actually one of the numbers. So when you take 16 out of 16, how much is left over? Nothing, just the B. Or we could say 1B. But it's usually just whenever you have a variable and a 1, you just put the variable. Now, how many times does 16 go into 32? That would be twice. So your greatest common factor in sum would be 16 times B plus 2. And that's all it is. Okay, again, if you want to do all three on your own, pause now and then come back and see how you do. Otherwise, let's go through 7 together. So let's find the greatest common factor of 6 and 8. So 1 goes into 6, 2 goes into 6, 3 goes into 6, 6 goes into 6, and then there's that little y kind of hanging out here. For 8, 1 goes into 8, 2 goes into 8, 4 goes into 8, 8 goes into 8. So what's the greatest number they have in common? You guessed it, it's 2. So we pull the 2 out, and we know the y has to go down here. But how many times does 2 go into 6? That would be 3 times, so it's 3y. And how many times does 2 go into 8? That would be 4. So that's your answer. Go ahead and work on 8 and 9. Come back when you are done. Good luck. All right, so for 8, the greatest common factor of 25 and 15 is 5. So when you pull that out, 5 goes into 25 5 times. That's how I got 5 plus. 5 goes into 15 3 times, and I had to bring that variable down, x. So I put it right there. Just kind of tags along. It's like a little brother. Get away. That's all mine was. Anyways, for 9, I decided to do the prime factorization method just because I wanted to. I saw that both numbers share they share 2 2's and a 3, and that gives you 12. So I put 12 on the outside as the greatest common factor, and 12 goes into 36 3 times along with the little brother n added there, plus 12 goes into 24 twice. So that's how I got those answers. Hopefully you got the same answers as well. So sometimes it may say write 4 equivalent expressions, meaning can you write it 4 different ways? Well, one way that everyone can always write it is the way that it was already given. So 9 plus 15, that already counts. Then from there, pull out the greatest common factor and see what else you get. So if we do that, if I pull out the greatest common factor of 9 and 15, they both share a 3. So the second way that you could write it is using the greatest common factor in sum, which we just learned. So when you pull the 3 out, 3 goes into 9 3 times, and 3 goes into 15 5 times. So that's how you get that. What's a third way? Why don't we just flip-flop 3 and 5 and write it as 5 plus 3? Same answer, same results, different way written. And the fourth way is, once you pulled out the greatest common factor, add 5 and 3 together and you get 8. Every single one of these gives you the same value, which is 24. So all four of them are equivalent because they give the same answer. So write this down as an example that you can see, and then we're going to work through a couple here. Now here's the first example I'm showing you where both numbers have the same variable. Whenever both or two numbers have the same variable, you can add them, you can subtract them together because they share that common variable. So the one way you could write this would be 25m minus 5. Now you can't flip-flop the subtraction sign, but we do know that if we subtracted 25 and 5m, the second way would be 20m. The third way, and the most simple way, is let's find the greatest common factor and sum. So what's the greatest common factor of 5 and 25? That would be 5. So they both share an m, so that would also be part of the greatest common factor of 5m. Now what's left over? How many times does 5 go into 25? 5 times. Keep that subtraction sign down here. And 5 goes into 5 once, so you leave the 1 there. So that's a third way of writing it. Then the last thing you can do is subtract 5 minus 1, which gives you 4, times the greatest common factor of 5m. So that's your fourth way. You can get creative with these in trying to solve them. The biggest thing I'm trying to look for is that you can look at two different terms and be able to change them in different ways of getting the same answer. That's what I'm looking for from you. All right, so on your own, I want you to find 4 equivalent expressions of 16 plus 30, 34 minus 4, 18x minus 12. So simply put, you could try to add or subtract them first, and then you're going to work through the greatest common factor and sum and rewriting them different ways. Good luck. Come back when you got them. Oh, before we do that, let's do 13 together. So the one way we can rewrite this is let's just add them together. 30 and 16 give you 46. The second way to do this one is find what the greatest common factor of 16 and 30 would be. And the largest number that 16 and 30 share together, sorry, I had a little coughing fit there. The only number that's great enough that they share in common is 2. So how many times does 2 go into 16? That would be 8. And how many times does 2 go into 30? That would be 15. The third way is, let's just flip-flop the 8 and 13. So 2 stays the same, flop 15 plus 8. And don't forget the fourth way, we keep that greatest common factor out there. Let's multiply it by the sum of 15 and 8, which is 23. So that is how you can get 4 different ways of getting the same thing. Good luck on 14 and 15. Come back when you are done. All right, so these are different ways to write 14 and 15. I had fun with both of them since they're subtraction. So I just inversed the subtraction to be addition, and then I found the inverse, whatever this is. Get out of here. So I had fun with that. But the first one I did for both is I just solved it. The second one, I found the greatest common factor. For 14, it was 2. For 15, it was 6x because they both shared an x. And then I showed what was left over. And then for 3, I just solved what was in the parentheses and wrote that next to the greatest common factor. And then for the fourth way, I just flip-flopped the numbers because it really doesn't matter which order you do them in. You probably came up with some other different answers, but hopefully you came up with very similar ones to what I had. All right. I think that ends our practice stuff. Let's get into the last part of the lesson. All right. Now that you've looked at all the stuff we've done in this lesson, describe different ways to write an equivalent expression. So how do you know the different ways? And then for number 2, explain why the expressions 15 or 5x plus 1 and 5 times x plus 1 are not equivalent. Go ahead and try to explain that one to me, and then you can move on to the quiz. And again, if you're stuck on these, come see me. All right, here is your quiz. You got 4 problems, and all I want you to do is find the greatest common factor in the sum. I'm not even going to worry about messing with finding equivalence. Good luck. Come back when you're done. All right. Good luck, or I guess you're done, so no more good luck. I'm glad you joined me. We'll see you next lesson. You did a great job getting through all this work.